Hello and welcome. This is CSE 228. Here we are both virtually and in person. So this is Agile Hardware Design grad course. I'm the instructor, Scott Beamer. This is a fun course. I'm always excited to teach it. It's an elective course. Despite being labeled a graduate course, we're happy to welcome undergrads to it. Um, so let's get to it. Today, in the first lecture, we tried to hopefully motivate the course. Why are we doing all this? Um, Talk about Agile hardware design in general, also get some logistics. And actually, before the end of the day, we'll see a little bit of code. So why even do this in the first place? Well, as we know, we are in an extremely digital era, right? The buzzword from years ago was ubiquitous computing, and computing is so ubiquitous that it seems silly to even mention that, right? We have it all around us, whether it be our smartphones we carry with us everywhere, or even other, small Internet of Things devices attached to us at all times. It's even inside of things like toothbrushes, for example. It's in our car, it's in data centers everywhere. So there's all these electronic devices. They're, of course, all powered by chips. So the question, of course, is where do those chips come from? And the answer is someone has to design them. And with all these different applications, we need to design chips for all different places, right? All different applications. And so multiple forces kind of at work here. Number one, of course, you may have heard in various courses about Moore's law, the property of, as time goes on, advances in chip manufacturing allow us to provide more transistors for less money. In other words, for a reasonable amount of money, the amount of transistors we have access to keeps increasing. This has been true for decades. And as you've probably seen in news headlines, it's starting to have some slowdown. There's been some hiccups. But whether or not Moore's law continues or slows down, for almost 20 years now, we've had a real big energy challenge, right? And that is that for everything we want to do, requires computation. Computation requires energy. As we try to do more computation, that will require more energy unless we improve efficiency, right? And so thus, in order to get more done, we have to keep improving energy efficiency. And so much of hardware design and architecture is really predicated on how do we improve efficiency so we can get more done. And one of the most classic ways to improve efficiency is something called specialization. That is, rather having a general purpose processor that can do anything, we tailor the hardware to do just what we want to do. So that's streamlining that specialization, makes it more energy efficient, but it, of course, also has certain consequences. Shifting over to the design side. Okay, so we want to build more specialized chips. What does it take to make these designs? Well, as these transistors get smaller and smaller and smaller, it actually gets harder and harder and harder to design them. Even though we're using lots of tools to help us, all sorts of constraints emerge, and so the cost of designing a chip just keeps going up and up and up. And so, wait a second, we're in a world where we need more specialized chips. However, at the same time, design costs are rising. So how do these two worlds become reconciled? Uh, if we don't figure this out, we have this horrible outcome of wait, we can't afford to make the chips we need, and everything kind of slows down, right? We can't build enough efficient chips. All these things happen. And so the good news is that's not what's happening. What's happening is that as a community, we figured out how to design chips more productively, more efficiently. And so as a result, we're able to get that productivity and that efficiency there. At the same time, with things like AI, there's never been more demand for custom chips. And so there's this massive incentive to figure this out, and people are figuring it out. And so I created this course originally 4 years ago. In that time point, someone like Google was maybe the only cloud company doing their own silicon for their own data centers. Here we are 4 years later, they all have their own custom silicon, right? Google, Meta, Microsoft, Amazon are all deploying their own chips. And these chips cost a lot of money to build, but they deploy them so widely, it pays off for them because they're specializing. And so we're talking this course about how do we design hardware more efficiently? How do we do that both to make efficient hardware, but also to make that process more efficient? How do we go about designing these chips? And so to go about that and to kind of get at the panel for this course, you think of designing hardware in two different styles. And this is not even just hardware, but more generally engineering. The classic way to think of engineering is what we call the waterfall technique. And the way I think of it is, it's very careful planning, and you want to make sure you make no false steps, right? You want to make sure everything is correct. You don't want to get anything wrong. And this has been very successful in some domains. Take civil engineering, for example, right? Hundreds of years ago, periodically, bridges would collapse. Civil engineering got much more better, much more rigorous, and was able to prevent that. And now these failures are very rare and highly documented because they're so rare, right? And so what do? You have very careful plans. So imagine you're trying to build a dam. And so you're going to do all sorts of modeling and surveying and Alternate tests, every step of the way, you're going to be very careful. You're going to build and test your molds, doing all right. But if you get it all right, you have a correct dam and everyone's happy. But it's this key constraint, right? When you're building a dam, you can only pour the concrete once. When you poured, millions and millions of gallons of concrete, after a dam is built, you can't decide, oh, I want this dam to move a foot to the left. That's not going to be possible, right? So what's the alternative? The alternative is something called Agile, right? Which is this notion of embracing kind of continuous changing and adaptation, right? So the Agile philosophy is you can't know the perfect design in advance. And so you need to kind of continuously adapt, right? And say, you know what? Well, here's what we believe to be best plan so far. Agile doesn't mean there's no plan. It just means you're very willing and able to change your plan along the way, right? And so think of that, as an example, as a competitive athlete, right? Of course, you're going to train, you're going to be in good shape. Um, when it comes time to compete against another opponent, how could you possibly know what they're going to do in advance? You can have some hunches, you can have some plans, but you're not going to know for sure, right? Instead, what you're going to do is you're going to recognize what they do, adapt, and then outcompete, right? And so that's kind of these two styles. And you can see that both of these philosophies actually have their domain, and which one's appropriate for your domain depends on the constraints of your domain, right? For situations where you only can do something once, I would highly recommend the waterfall style design approach, right? If you're looking to pour concrete once, you don't want to, pour concrete and have somebody tell you, you know what, let's move it over a foot. You can't do that. However, it turns out things involving software aren't like that, right? Um, you can continuously adapt and revise it, right? For example, we're taking it for granted now that so many applications we use, whether it be in the cloud or even mobile, they almost aren't even publicly versioned to us as users anymore. We can't quite even tell sometimes what version it is because it's continuously adapting and revising, right? And many of you are too young, but when I was very young, we had these massive waterfall efforts. Microsoft's released this brand new OS from scratch. They're doing all these things from scratch. There's so many catastrophic failures in software in the waterfall because it turns out this adaptive thing is much more efficient when you're able to change. And so the whole premise of this course is, you know what? If we're able to recognize aspects of hardware design that can make it easier to change, not set in stone, and easier to move, we can embrace an agile philosophy. And the agile philosophy, we're able to much more able to adapt to what we need to do. And it's not just going to be less designer effort; it's going to be more productive, and that will kind of come together. Okay, so taking those philosophies in the abstract and now bringing them to what to look like in practice for hardware design. Traditional hardware design, you have this very deliberate process, right? One step at a time. You complete one step before moving on to the next step, right? So you're going to design your chip. You're going to specify all the pieces, break it down to all these blocks. Each of these blocks have certain components and rules. You're going to go off and task teams implementing those pieces. Each of those pieces is going to be tested in isolation. Then you start integrating them and start testing them again. After you've kind of started, after all those functional pieces kind of coming together, they start trying to optimize them, perhaps individually and integrated. And then finally, you verify the whole thing, right? And so this works. This is how we have functional chips. However, it doesn't allow itself very easy to changes, right? Imagine more agile hard design philosophies. You know what? We'll get a design running, we'll implement something, we'll optimize it, we'll verify it, but then we'll go ahead and just keep tweaking it. And so you know what? Each time in the way, we'll look at what we didn't like about it and go ahead and change the design, change the implementation, optimize it, and of course keep retesting it and keep going through this loop over and over again until we find something we like, right? And if once we're satisfied with it, we can stop. With a waterfall, it's a little bit hard to know how things are going to end up in terms of performance, power, or area, right? Those are the main metrics used to evaluate hardware. You can do your best to model things. You can kind of set budgets for certain things, but until you have the entire thing integrated, you don't know for sure if you achieve those targets, right? Versus with an agile approach, you go through the entire process often. So you always know where you stand. It may not be great. Maybe your first design, because you did a really simple design, it's not optimized to get us through the tools. It's not optimized. The numbers aren't good, but you know those numbers are, right? And you can go ahead and optimize and target it. And so you may see me in this course kind of constantly making this circular motion. Um, and that's because I'm talking about going through loop. That is a loop of the design process as well as using the tools. And that's kind of the key point of this course that you can see as a course logo. Also put out there for folks who have any kind of questions or comments. I very much encourage discussion. For those of you in Zoom land today, you have to speak up because I can't see that Zoom screen right now. Um, that's where we are. Okay, so this is kind of just laying out the philosophy of waterfall versus agile. The goal of this course is to be more agile. I'm kind of almost sometimes doing a caricature or an over exaggeration. But one takeaway from this course for you is hopefully recognizing when can you utilize agile ideas to kind of go better for your own application. Cool. Okay. So um, why is Agile, like I said, so helpful, right? And the answer is recognizing when you have a situation where you aren't set in stone, you can actually repeat things. Things like software, or in this case, hardware design, you can just run the compiler again. You can run the tools again, right? Um, and so as a result, you're able to kind of keep redoing things. And like imagine trying to build a hardware chip. Um, when you first start drawing out blocks and components, you may not know what your critical path will be, right? It's not until you push this through the tools and actually done a placement and routing that you know what the critical path is. And guess what? You can look at that critical path. Maybe that time it takes to delay is fine. For performance, that's satisfactory. You can be done early and be done, right? But if not, you can go ahead and attack it and go after it, right? And so there's so many things when it comes to hardware design, it's really hard to know until you start actually getting your hands dirty in the process. And that's what makes Agile so good for hardware is you can know how you're going, right? You can see how it's going through the tools, what kind of performance metrics am I getting, et cetera. Also things like verification, which typically in the practice industry is this kind of adversarial teams approach where designers get to write whatever hardware they want and chuck it over a wall to verification engineers. The verification engineers are just burdened with all this RTL to go ahead and verify. And you may have heard in software it's very common to have a 1-1 ratio of engineer to verification engineer. In hardware, it's very often only one RTL writer to two verification engineers. And part of the reason why is people writing the RTL aren't the ones writing the verification collateral. They don't even test it sometimes. It's just kind of, chucking it over the wall. That's not great. An agile approach kind of bring verification into the process earlier, bring testing into the process earlier, making sure we're kind of all on the same page. And so as I keep saying it over and over again, agile has already been proven for software. And I should clarify, when I say agile for this course, I'm talking about this kind of iterative revising approach. I'm not really worried about, things like scrums or velocity and that kind of stuff. You've seen those terms, like, the agile trademark, stuff. But more generally, just the notion of just embracing revision, adapting your plans as you need to, right? And so that's what we're going to do in this course, right? How to view hardware designs from a more fluid and flexible approach. Um, and what's interesting is, if you look at what will enable this, well, the language that's commonly used, Verilog, I actually argue is like pouring concrete. Um, that language builds very functional and correct hardware, but it's actually hard for humans to get it right. That language, despite the specifications being over 1,000 pages, has plenty of behaviors that are undefined. And so as a result, in order to make this code robust, people who write Verilog are constantly using things called linting tools that check their code for things that aren't against the rules of the language, but lead to more safe behaviors. So it's this very careful, deliberate process of writing the Verilog. Once it's correct, you don't want to mess with it. And guess what? Concrete, if it's the right shape in the right place, it'll last a long time, right? It's concrete from the Romans, right? Like concrete lasts tens of times. There was Verilog that's 30 years old, that's still being used today, and chips we're using today, right? The problem is that once it's all there, it's really hard to modify, right? Because it's not just a matter of how brittle is it; it's a matter of you're also going to change your verification, right? Someone to allow to verify that Verilog. Once you change that Verilog, you kind of break the seal on that verification, and now you have to re-verify all this. And so, what's enabling that you do agile design for hardware is actually new languages and new tools. And with new languages and new tools, much more able to kind of adapt and rerun things. Cool. So, um, why am I making all this, passionate plea for agile hardware design techniques, right? Number one, so the goal is reduce designer effort, right? Per hour of human working, we want to get more hardware components out there. And so part of how that's possible is we can focus the efforts to where it's needed, right? When you see the entire cost of your design, you will know where you are doing, where you hope to do well, and where you're not doing well, and how to go attack. And so you can go right to places needed. You're not going to kind of over-optimize certain places at the wrong times. It actually can lead to better results, right? One of the things that's really painful is, let's say you have this late integration of your design and you're way off your target for performance. That's really rough, right? There's only so much you can do at that point. You've already written all this RTL, you've already verified a lot of it, and now you need a massive change to your architecture in order to reach the performance target you want. That is a disaster, right? You're gonna do everything you can to model and plan to prevent that from happening, but if that does happen, you're in a bad place. Versus with a more nimble, agile approach, you can see how you're doing, right? And you can recognize how you need to change architecture early on before you even get to that place. And so it's really good at helping you kind of guide your optimization efforts, and you kind of have this not just modeling, but actually using the real tools and the real design to see how you're doing in terms of these things. And so as a result, in the software, Agile took over because it was very predictable, right? And have these massive cost overruns, massively delayed projects, saving shoot hardware, right? You have a design, it's constantly able to go through tools, keeping it simple to go through, going through design loop. You have a design, it's a question of just, is it as high performance as you want it to be? And if you need to, you can kind of keep adding things onto it. Cool. Okay. So, um, you're gonna hear me in this course throw out a lot of buzzwords. I want to spend a moment to kind of differentiate them. So this course is officially about agile technologies, right? And so agile techniques, right? That's rapid iteration, what we're talking about, etc. That is an orthogonal concept to open source hardware design. I'm also very passionate about open source hardware design. This course makes extensive use of open source hardware design tools, um, but these are technically orthogonal concepts, right? You can do agile with closed source tools. You can do waterfall with open source tools, right? Um, And of course, you also, which is very common, you can mix both proprietary tools and components and open source tools and components in the same project, which is typically done. Um, so these are two orthogonal concepts, but for this course, yes, we're excited about Agile, and everything I teach in this course is open source, but you, of course, can apply to closed source tools as well. Um, and so why am I so excited about this as an academic? I feel like this really enables to kind of democratize hardware design, where for a long time, hardware design was kind of constrained to large companies with expensive commercial tools. Now all of a sudden, the tools are free if you have open source tools. So wait a second, you're only a big company. You don't need a big licensing fee to access these tools. And then with Agile, even small teams or even an individual can actually get a lot done. And so all of a sudden, wait a second, the barrier to entry is just so much lower. You need a much smaller team, so much less cost to do it. So now with reduced costs, you can have a lot more people producing hardware. And they can produce hardware that may match their scenario. You may be in application domain, you've been part of the world that's neglected by the current offerings. You are now enabled to go out there and go do that, right? Free tools makes it low cost to enter. And of course, Absolute makes you productive when you're doing it to a smaller team. And this is great. I'm really excited about this as an academic, right? We can get a lot of people involved in hardware design, get a lot more voices, include a lot more people, get more creative designs from this kind of stuff. Cool. Okay. So uh, the pedal is a way to fly, but as you know, what is the fastest hardware block to develop? And of course, the answer is it's the block that you get to reuse, right? Rather than having to write the block out, you say, no. I just go to my library and grab this block. It does what I want. This is the standard practice of hardware design, right? People will license IP. IP, of course, being short for intellectual property. As existing hardware design, they will license it for someone else to put into their chip. That works great in a lot of places. But there's some caveats, right? If you're going to reuse some component, it better do what you need it to do, right? And this is where this is the trick, right? Um, if it's 90% of what you want, that sounds like you're close. Oh, I'll go ahead and just change that last 10%. Sometimes that's really painful, especially if it's in Verilog. It's hard to kind of make those tweaks and those changes. And so to get reuse, you want to make sure the thing you're trying to reuse does what you want to do, does quote unquote the right thing. But also, let's say someone does give you the IP. If you're going to check into your design, you want to make sure it's correct, right? You want to make sure this is going to work. Um, and so how do you get that? There's one thing for it to be correct. It's another thing for you to have the confidence is correct, right? And so how do we achieve these things? And so that's the goal for reuse. We want to have something that is the right thing we want to do and that is correct and we have confidence is correct. And if we achieve all that, great. We can reuse these components, make our hardware design process a lot more efficient. And then as a hardware designer, I can spend more time on what is novel and unique for my design and less time reimplementing the wheel of rebuilds. And you'd be surprised how often when you go look at various companies, they all have their own internal libraries of components. And these components look extremely similar because you have these various things. There's crossbar 4 ports, crossbar 5 ports, crossbar 6 ports, etc. And the reason why is you want to get the exact right combination. You'd be surprised how often you kind of keep reinventing the wheel because what you want exists, but you want to just change it 10%. And that 10% change is surprisingly painful with traditional techniques. Cool. Questions so far? Okay, we can keep going. So I pitched this goal of really want to get reuse. And so how can we make reuse easier to achieve? And the answer is rather than having a single static component, which may or may not be what you need, we can have a generator, right? So that generator can make many components, right? And so generator is not going to be some sort of arbitrary, dream anything up and erase any kind of hardware. No, the generator is targeted. It has a certain component it's making. It just makes different variants of that component with some tweaks, right? And so you give it parameters, it churns and spits out code for you. And so that's what we're building in this course. We're building hardware generators. And that's the kind of idea is that with a generator, it's more flexible in a single static design. By being more flexible, it's more reusable. And by being able to kind of tailor it to our design, we're able to kind of use it in more places. And so what's kind of interesting about generators is in addition to being more reusable, they also help a certain open source challenge. And that is for open source, you can make whatever you want and put it online, make it open source, sure. But the really successful open source things have large community contributions, right? And one of the challenges, of course, is reaching critical mass, of having something that is sufficiently useful to enough people that you get a community willing to contribute back to it. And with a generator, because it's more flexible, it's thus usable in more places. And because it's usable in more places, it's thus able to attract a large community and thus have more people contributing to it. So there's a large community, you can have a large organization in this effort. I'm really optimistic for the future of hardware design generators being this way to kind of get open source hardware really out there. So the kind of key point behind these generators, really think of design generation as another step in the tool flow, right? Where right now, the tool flow, okay, yeah, I give the RTL to the synthesis tool, et cetera. Now, before RTL was going to be this design generation step, right? And so really we're writing programs that in turn are doing the hard design for us, right? And it's not doing arbitrary, whatever stuff. It's controlled. It's under very specific plans, but that flexibility will be really helpful. Cool. So how are we doing in this course? We're using a language called Chisel. So Chisel here is written as a normal word, but it's actually an acronym standing for Constructing Hardware in a Scala Embedded Language. So we use this language extensively in this course. I want to emphasize the purpose of this course is not so much learning Chisel as much as it is learning hardware design, right? In particular, Agile hardware design. Chisel happens to be a great vehicle for that. So what is it? Well, it's a hardware design language. Technically, it's a hardware construction language as a way to build generators. It's embedded in a language called Scala. So Scala is a extremely popular language in the Java family. So it runs on the Java virtual machine, the JVM. So anywhere you can run Java, you can run Scala. It has some nice features, right? It's got a strong static type system, has type inference. It also has, things like interpreters. You want to go ahead and try things out. In this class, you'll see me writing it inside Jupyter panes as part of lecture. Today's lecture is in Jupyter. All lectures are in Jupyter, as well as labs. There's something called Almond, which provides Scala inside Jupyter. So there's always kind of some nice software out there, right? And we'll talk more about Scala later today, but this kind of is fun language. And the reason why I got into the mix is Scala was made to make it easy to make new languages. So there's a lot of traits put in this language. A lot of the features of this language were designed to make it easy to make your own language. And so in this case, when researchers at UC Berkeley built Chisel, they found Scala was a really great place to do this. And so they chose to use Scala to embed their hardest description language in. Since Chisel, there's been quite a few additional next generation hardware design languages. And most of them are embedded in some other language, right? So they kind of have this embedded DSL approach. And so Chisel's one in this course, but now there's a bunch. 15 years ago, it was really kind of system Verilog or Verilog, and that was it. And now a lot of people are doing new things, which is fun, right? Trying new languages, doing new things. And so as you learn some software, as you learn more programming languages, it makes it easier to learn additional programming languages. The same is true for hardware. As you learn more hardware design languages, it makes it easier to learn additional hardware design languages. And what is Chisel able to do? Well, it's able to take the best of, software-oriented programming, such as object-oriented and functional, and bring those to hardware. It also makes it easy to make generators, where that generator idea I was pitching is a really strong idea. It's actually already widely deployed in industry with Verilog. And the question is, wait, how to do it with Verilog? Verilog is so restrictive. And the answer is they use a two-language approach, right? They have, whether it be Python, Java, Perl, or even Tickle, stitching together Verilog strings to generate the component they want. And so that works for things like a crossbar, where you can imagine how to kind of write those for loops to generate the strings of text you want to be the right Verilog. People do this. It's widely done in industry. However, you can imagine this is really brittle, right? You have one language, would it be Python or something, running a program, and then it's just putting together strings. It has no notion of what's in these strings, right? Versus using a language like Chisel, we're able to take a proper programming language like Scala, and done hard design directly in that language rather than with strings, a lot of things work out a lot better, right? You have all this much better, stronger type system. It's much more safe. Doing this kind of generation approach in a single language is a lot smoother. And so, look at all kind of the next generation hard design languages. Like I said, part of the reason why they're all embedded as opposed to standalone languages is because they want the ability to build generators. And so, yeah, Chisel, for those of you who aren't familiar, it was originally developed at UC Berkeley. Now it's widely used by a company called Sci-Fi, which is one of the main RISC-V companies. It had deployments from both Google and Intel and IBM. Not Intel, sorry. Google, IBM have shipped things with it. Intel has played with it and not shipped anything with it. So it's an interesting language. It's had some fun adoption. Like I said, for this course, rather than focusing on learning Chisel, focus on learning kind of this new wave of hardware design, this very software-centric style of hardware design. Chisel language for this course. You go someplace else in the industry, they may have some other next generation language you're using, but Chisel help you kind of get going. Cool. Questions on that? Yes. Good question. So where is Scala used in industry beyond hardware design? So Scala, like I said, it came out in the early 2000s as a way to kind of improve upon Java, and it had a lot of interesting ideas. Its initial adoption was kind of very esoteric. It was originally in high frequency trading in finance, and then Twitter. Twitter was a huge early contributor to Scala. They got really excited about it. And actually, if you look at Scala's language growth, I would argue three things happened to it. It was kind of victim of its own success. So Scala did a lot of things really, really well. What happened? Well, Twitter did really well with Scala. And so Twitter is like, well, gee, we want to do Scala well here. So we're going to go ahead and hire away to Scala core developers to our company. So Twitter took a lot of the core Scala developers from the language team to Twitter itself. That hurt the language, but also was victim of success. So you may notice that Java's not stayed put. Because, right now we have Java 24 coming out, right? And so Java keeps adding features. And looking at what feature the Scala has, you know what? That is a good feature. We'll do that. A lot of times, but by the time some of these features find their way back to Java, they're sometimes a little bit watered down, not quite as robust, not quite as, general or pretty in the programming languages theory sense, but they're getting adoption. The third thing that's also putting pressure on Scala, of course, is Kotlin, right? Where Kotlin's another Java language. It looked at what Scala got right and said, oh, that's great. We're going to do that, but simpler. So I would kind of think of Scala as like the highbrow and I wouldn't call it Kotlin lowbrow, I'd call it more efficient, right? It's kind of this very utilitarian language. But you'll see Scala is a very rich language. Um, and yeah, it is used in industry. It runs on a JVM. It's used in software. Twitter was the biggest user of it. Someone can correct me or in the chat or something, tell me somewhere else where it's used concurrently. Um, but yeah, things like Kotlin and honestly just modern Java have also decreased Scala's room for growth. It wasn't a very strong growth curve, and it kind of like went to medium level growth. Good question. And I should also maybe mention is that right now I'm being recorded. Uh, the emphasis on the word "I'm being recorded." The AV setup is such that the students are not recorded, and so I'm going to post this on YouTube. So I'm the only one there. That's why I'm using this to read a microphone because that way it doesn't pick up the student voices. So yeah, you can be asking me questions, and I'll be usually trying to repeat them for the recording, but your voice will not be on the internet. Don't worry. Great, cool. Okay, well, so what are kind of the main themes for this course, right? Uh, Here's my pictorial representations I've done. So you may see me making this motion all the time. That's the course logo. This notion of close the loop. When I say close the loop, I'm talking about that agile design loop. In other words, have some aspect of your design running in some sense with the tools, right? Whether it be running a simulation or even a physical design flow, get that to happen as soon as possible, right? Once the loop is closed and you have results, then you know where to spend your next bit of effort. So I keep talking about close the loop, keep making this motion. We're talking a lot about this course about how do you take your long-term design goal and simplify it such you can make something really small to close the loop early and then progressively add on functionality or optimizations to get to where you want to be. Um, as you've already seen, of course, from the prior talk, I'm very excited about reuse, right? The whole point of these generators. And so how can we design our components to be maximally reusable, right? That's designed for reuse. The third one, hopefully, is self-motivated, right? Make tools do the work. So AI is not the first form of automation, right? There's plenty of automation in hardware design. If you look at the history of hardware design, look at the first transistor designed by approximately a dozen people. So, okay, 12 engineers to one transistor. And now you have like the latest, chips from Apple, which have tens of billions of transistors designed by a team of hundreds or maybe a few thousand engineers, right? So you can see in terms of transistors per engineer, the numbers through the roof, right? That's only possible because of design automation, right? There's all sorts of software doing this automation. And so the goal for this course is to recognize what these tools can do, what they provide, and how do we best use them. In this course, we're using this privileged chisel language, which makes it easier for us to build hardware generators. And we can take things that normally humans have to do and now pass it on to the tools. Of course, many people are very excited about AI. AI is going to definitely help in hardware design. Once again, another form of making tools do the work, right? Embracing automation. And then the fourth one is, part of what you're getting by a human taught course, designed for readability. As you're all aware, code is typically read far more times than it's written. And so we'll be talking about how can we structure our designs, not just be, higher performance or more robust, but also just how to make the code more readable. And so you're going to be getting a heavy dose of my opinions about what I think makes code more or less readable. Hopefully, some that you will agree with, and some that you disagree with. And that's good. Have a discussion. I'd love to have debates. Cool. And so, yeah, this is the material we just saw on the prior slide, written out in textual form. But yeah, these are kind of the course themes, right? Closed loops are the most common one we were talking about. Make tools that work. How can we figure out things that we as humans do that can offload to the tools? And then, of course, how do we make our designs both reusable with generators, as well as make our designs easy to read, the actual code itself. Um, Great. So now getting to the more logistical aspects of this course. Who should take this course? Number one, people who are excited about this material. Um, I kind of pitch it as there's three domains of prior experience that are helpful. So one, of course, is hardware design, so using language like Verilog or VHDL. Here at UC Santa Cruz, these are taught in courses like CSC 100 or 125. Right now is of course 225, which is a graduate version of 125. That's not just sufficient; it's overkill. So if you're not taking 225, that's fine. You're totally ready for this course. Um, Architecture is helpful, right? Understanding what we're trying to build in hardware is useful. So, for example, here at Santa Cruz, as are 120 for undergrads, 220 for grad students, um, understand in this course, I love building processors. I love building RISC-V processors. That's not what we're going to do in this course. We're going to build ultra hardware designs, but I deliberately don't build ISA-driven processors for a few reasons in this course. Number one, there's a lot of interesting hardware that is not processors. But number two, processors kind of all these things where it's like, okay, we know the processors. We know you want to build a certain number of stages or certain techniques. So in the end of the day, there's actually kind of much more constrained space. And you'll see that by taking a much more broad view of hardware beyond processors, we actually have a lot more fun opportunities to try new things. And so yeah, so being overly dependent on an ISA, something I deliberately did not do for this course. I don't want to be an unnecessary barrier. So yeah, so when I say architecture, I just mean familiar with hardware in general. You understand, what the difference is between a logic gate versus a register, what a mux is, how kind of things fit together, that sort of stuff. Um, and then advanced programming. So in this course, we're going to take advantage of both object-oriented programming as well as functional programming. And so those are kind of what we're trying to do. And so let's say here, hopefully experience with two of the following. If you have all three, that's fantastic. You're already kind of a rare person because usually you can see, depending where you are in this list, that's either more of electrical engineering, computer engineering, or computer science training. And the goal of this course is to kind of bring these worlds together. And so I've been very grateful for this course. I've been able to attract students from all these different domains. And so, yeah, keep it coming. If you experience with 2 out of 3, you're in great shape. If you experience with 1 out of 3 and you're interested, we can probably make this work. I've had students in this course that were completely inexperienced with hardware. They were graduate students, two of them, that had come from industry to come back to get the graduate degree. They had not taken any hardware design courses or any architecture courses, but they were professional Scala developers. And so, yeah, they thought this course was interesting. They read the Scala source code for Chisel, and they were, off and running, had a really good time. And so, yeah, I want to make this course inclusive. Happy to talk more about people, what they feel their backgrounds are. That should be good. The goal is to make this, a big inclusive course. That's why we have undergrads in this grad course, et cetera. And so, even this course is not only about, hardware design, hopefully you can kind of embrace these agile techniques and see where they apply elsewhere. Cool. Okay. So who am I? I'm a professor in computer science engineering here at Santa Cruz. Um, I'll be available to answer questions for today's lecture. But every week I'll have office hours 3 to 4 in my office. What I do for research? I'm computer architecture. I do work in open source hardware design. I do stuff in high performance graph processing, more in the high performance computing domain. Yeah, this is definitely the kind of stuff I work on, and it's really fun. Um, as you're aware, this quarter, unfortunately, we do not have a TA. On the plus side, after years of running this course, we have enough automation. I think we'll be okay. So um, please reach out when you have any concerns about getting help in the course. I'll do my best to help you. But also, you talk to each other, right? There's the class as well. Um, how is this course structured? Well, this is a passion project for me. This is a elective grad course. So I'm trying my best to make this fun and interesting. We make this available to undergrads. Um, and that's kind of cool. We get to, I change the content to what I believe to be the best and most useful stuff here. And so how to go about this? Well, there's kind of two portions to this course. There's a structured portion where you're gonna have lectures like today. Uh, you know, Even though it's two class meetings, it's kind of like three lectures a week in a way. Um, and then that's gonna go on for the first 2/3 of the quarter. And then we will shift gears to the project portion. So the whole point of this course is really the project. And the stuff before that's kind of just training you to get ready for the project. This is the plan. Of course, we'll always be changing and adapting as needed. For example, one thing that came up is, one of my colleagues has a course that has the exact same time slot. There's a lot of undergrads who want to take both courses. So working with, um, great. Yeah, so you can see, how does this actually boil out for our course structure? Um, like I said, lecture, we meet in person. I'm also putting recordings online. So watch however it works. I really appreciate an in-person audience. I really appreciate in-person questions. But, people have constraints, understood. Actual course work, there's three types of coursework. In the structured portion, you're going to be doing labs and homework. So one lab per week, one homework per week. The labs are designed to be easy, lightweight, kind of directly try out some feature and kind of quickly in isolation. The homework's a bit more involved coding. And so that's the initial portion of the course. Then you shift gears to the project, right? The project's gonna be, this big project you build either in isolation or a partner. I'm gonna encourage partners, but not strictly required. Um, Along the way for the project, we're gonna have some scaffolding, right? We're gonna have, proposals, some feedback, code reviews, etc. But ultimately, you are building a project which is gonna culminate with presentation. These are kind of the main things we'll be doing. You may notice, for example, on this list, what's missing, exams, right? Elective grad course, I'm not required to have exams. I think that's really a weird way to evaluate this material. As you can see, based on the point weighting, as the percentages in the lower left, this course is primarily weighted on your project, right? So hopefully folks build great projects. Um, cool, so lectures, here we are. As I said earlier, I recorded these, I put these on YouTube. I have the audio set up correctly such that students are not recorded. I'll double check if I need to mute for the Zoom. But that's where we are. Now, this course has historically been taught with a 3 lecture per week format. So the content's kind of diced in these very nice, tidy 60-minute lectures. And so as a result, what I'm going to do this offering is I'm going to try to keep those lectures contiguous and just have the middle one split in half. So you're going to see me talk for an hour, time permitting, take a few minute break, then talk for another half hour for half a lecture, and then you'll see another half lecture next time, and then another hour lecture following that. And so that'll kind of be that. For those of you watching on YouTube, we'll see how well I can figure out the YouTube editor. You may see 2 videos for those split lectures, or you may see me modify the video after it's posted to go from all of a sudden 30 minutes to 60 minutes. As I said, I kind of just set up for recordings. For those here at Santa Cruz, I also have the room lecture capture enabled as kind of a backup system. So yes, those of you who are in Santa Cruz and enrolled, you can access those recordings as well. But for the YouTube content, I just have a special setup on my computer for OBS to keep the students out. But as you notice, these lectures, this is all Jupyter. And so we'll be uh, doing that for lectures. I'll be running code in a minute, but also for things like labs as well. And these lectures, everything's open source. It's on GitHub. You can go ahead and, clone it, modify it your own heart content. You can, take notes in line. You can modify the code as I'm talking about it, etc. Whatever you find most interesting. How about the labs? Like I said, they kind of let you try out some focus features in kind of a concentrated setting. So rather than having to write out lots and lots of code, small snippets at a time. Okay, here, try out this 1 line, 2 line solution to fix this one thing. So free to do some groups, right? Have a partner, talk it over. Hopefully, these add most an hour or 2 per week. These aren't supposed to be super draining. Just a chance to kind of try out the features in isolation and get going. How are these actually done in practice? Like I said, it's a Jupyter notebook that's actually going to be running the chisel code. You're going to submit these online through Gradescope. They'll be auto graded. So in some number of minutes, you'll have your score. And so you can see, oh, wait, I got something wrong. I can go ahead and fix that and try it again, right? And so I recommend people do the labs as soon as you feel able to do the labs because, they're kind of the first step for any given bit of content. Um, cool. The homeworks are more substantial, right? So these are going to be, writing out code. You probably should use, uh, like an actual environment. I recommend for this course using some form of IDE. For example, IntelliJ, something for Scala. Um, a lot of people like VS Code. That's great. But anything that has something that gives you, not just syntax highlighting, but also code completion and, inline errors and warnings for syntax errors, that makes you so much more productive, right? Except for this course, make tools do the work, right? Why wait until compile time to find out you have a syntax error? Have that underlined right away. Um, for these homeworks, yeah, you submit these also on Gradescope. They're also going to be auto graded. We'll provide you some test cases. Test cases we provide you initially won't be all the test cases you need to actually have a correct full point solution. So along the way, of course, you need to write your own test cases um, and such. Now, when it comes to allowances for people who have understandable tough circumstances, for homeworks, we have what we call slip days, where you get 3 slip days for the quarter. They're, discrete integer quantities. And so whatever the deadline is, if you turn it in late, um, you can use that many slip days, right? And so this is there to kind of have that slack for whatever you need in your situation. The reason why it's only 3 days rather than, let's say, 20 days is because, yeah, we do want to keep people on pace. And so that way you're able to have sufficient time to do the project. And kind of the structured portion starts this course off is all about getting people kind of there. And that way, when you get to the project open-ended, you have, that background and that pace. And so, yeah, obviously if something more substantial comes up, talk to me. We'll see what we can do. Cool. As I said, the project really is the whole point of this course, right? That's what we're trying to get people to do. Taking together all skills we've done. I really recommend working with a partner. When the course is larger, I kind of insist on it because that way there's only so many time slots for presentations. This quarter, we have a medium number of students enrolled. So I think if you're really determined to do it by yourself, that's possible. But I think a partner makes it better. Um, so what are you going to do? Well, you're going to propose a custom hardware generator and you go off and build it, right? And so through covering this course, you're going to have not just the technical skills to write the code and that sort of stuff, but also talk about the design approach. How do you figure out what the minimum viable thing to get started is, and how do you kind of extend that and elaborate that? And so we'll talk about the project more as the quarter goes on, but there'll be support along the way. We'll have things like project proposals and meetings with the class staff to hear about how to tweak your project and stuff like that. At the end of the term, you'll be presenting your project to the class, submitting the code to the staff to be evaluated. Um, you're encouraged but not required to open source your project. And you can see on the webpage, I've linked all the prior project students who open sourced. And so it's kind of fun to see that. There's now a growing library of Shield projects and students in this course, and you can add on to that list. Um, how do we get resources for this course? Well, we have a variety of web presences. The number one place to go for most stuff is the course website. It's a public website, static HTML. Everything's up there. It's got links to all sorts of stuff, whether it be lectures, recordings, assignments. I also have some additional content I wrote up there about, here's some links for how to install Chisel or various tools and that kind of stuff. And that's totally open on the internet, right? So anybody watching it on YouTube, have at it. Um, for those of you here at Santa Cruz officially enrolled students, we have a Canvas. The only thing Canvas really does is tell you your grades and give you a way to submit assignments via Gradescope. Um, so in terms of course content, that's all in the public open. Uh, in terms of course communications, for people in the class, we have a Slack. And so I think many people have already joined that. It's linked. The Slack invite link is available on that Canvas webpage. And yeah, it's a way to get help. There's channels for different types of assignments. You can ask of your classmates. I try to answer whenever I can. It's a great way to get help. And so yeah, you can see this kind of both web pages under continuous development. You'll see me updating them both. Primarily the public web page, the Canvas site, as I said before, is mostly a way for you to kind of see your grades and submit assignments. Cool. Questions on that logistics? Yes. Oh, yeah. So in a project, you'll be picking a topic. If you find yourself unsure, uh, great conversation for office hours. We can help you iterate on your idea before you pick for sure. We also occasionally have some ideas of our own. Like, if you have, you're like, you're totally something like I have no ideas, and like usually I've given students these initial ideas we have, they've taken it and then changed it, which is great. We want people to have their own creativity, their own ideas in these projects. And so you can see from the past projects, it's all over the place. We have people doing things like the calculations for GPS or for like, a cell baseband. People build things that aren't even reasonable hardware, but it's kind of fun. Like they built like a Mandelbrot fractal generator, right? That's kind of fun. Good place to use generation. We have people do the game Snake, right? Why not? Have fun with it. So yeah, it's definitely kind of encouraging to projects. But yeah, I do want to encourage people to kind of approach these projects. So definitely engage that dialogue with faculty and staff. Well, I keep saying staff is a reflex, but unfortunately this quarter it's just me. Um, have a dialogue about what goes into your project, what you're interested in, and make sure it's sufficient. When it comes down to grades for this course, usually people, because there's auto grading, can eventually figure out how to get their homeworks and labs mostly correct, right? You get multiple submissions, you can tweak that out. I think our students get in trouble is when they have a very, very, very demanding course load. They have not enough time to do the homeworks, and so even though they can see when homeworks aren't getting correct, they don't have time to fix it. That's a problem. The other problem we had a little bit of last spring, our last winter, a year ago, for the first time in 4 offerings of this course. Some students did projects where the initial goal was pretty unambitious. That feedback was given, and then they didn't even reach that initial goal. And so as a result, they had a so-so project, so-so grade. That was unfortunate. So my goal is really have people doing projects they're excited about, they really are vibrant, and that's kind of the whole point of this course. Um, so wrapping up the logistic portion of this lecture, and we'll see how we're doing on time. We're doing fine on time. Um, we can break the course objectives down into both what is concrete, what are very measurable, direct skills, versus what is more meta, is kind of more abstract. For the concrete, the goal is for you to have an idea for hardware and actually build a working hardware design as a separate project, right? I want to build hardware that does X, and to actually go out and be able to go build hardware that does X, right? And so, what's required to do that? Well, you can say yes. I can go out and build, a hardware generator. I can figure out how to do things in Chisel. There's a lot of sub skills in there. How to use these various languages, these various tools, etc. But um, these are all learnable skills, and we're going to cover them in this course, right? And perhaps you can think about how to not just make a single instance, but how to make it like a generator that has the right amount of customization to handle the situation. Now that's the concrete direct skills from this course. The more abstract meta skills is really kind of viewing hardware as opportunity to bring programming in. Um, so rather than just this waterfall approach of I'm going to give it a spec, I'm going to write Verilog that matches the spec. Take a much more expansive view to hardware design process and understand how I can really build a much more efficient system and have this more agile, adaptive approach, right? And so, how do I go from an idea and start working on it to actually have something that's actually released and complete? How can I, break apart my big, complicated idea into small, bite-sized pieces and then iteratively extend those until it's sufficiently capable? And how can I apply my agile ideas elsewhere and such? And so that's kind of it. So great. Any lectures on the agile stuff or logistics? So I think we have the time budget. So I'm going to go ahead and stop the recording here.